Good morning, everyone. I'm super grateful to be here to talk about the ups and downs of AI in healthcare. Healthcare is a topic that people are interested in, which means that from time to time I get some tough questions. For instance, this summer I was climbing with a friend of mine, and he asks me, "Hey man, why haven't we cured cancer?" It's not the kind of question you're expecting when preparing to go up a 20, 30-meter wall. I tried to explain him that cancer is not one pathology, but in fact an umbrella term. It's an umbrella term for many diseases, of which we don't know much, in fact. The next quote sums it beautifully. Does it? Here it is. That to confront cancer is to encounter a parallel species, one perhaps more adapted to survival than even we are. This book, The Emperor of All Maladies, is an amazing book. And the quote itself, I actually stole it from the previous speaker, because her team has done, or is doing, amazing work in reality-centric applications of AI in oncology. The kind of applications or the kind of research that will better help us understand the problem at hand. And as people say, a problem well defined is a problem half solved. So let's try to understand better the problem of cancer, more specifically prostate cancer. 1 in 8 men are going to be diagnosed with prostate cancer. And although it is an indolent cancer, meaning it doesn't spread as fast as other types of cancer, in the US alone, every hour, 4 men die of prostate cancer. Right now, what are we doing to tackle this problem? Let me introduce you to the prostate cancer pathway, a set of best practices and clinical guidelines that define diagnosis and treatment. This usually starts with patient symptoms, either pain or blood in urine. At that time, the patient goes to a GP, where they're required to do a blood test. From that blood test, we get a PSA score. PSA is the prostate-specific antigen. It is a biomarker for prostate cancer. It is not super sensitive, it's not super specific, but when the score is high enough, we then go into the patient goes into a MR exam. In the MR exam, the radiologists will output the PIRAT score. PIRAT score is the probability of having prostate cancer. Now, once again, if that score is high enough, the patient does a biopsy. The biopsy is the definite diagnosis of clinically significant prostate cancer. Well, if this is the definite diagnosis, why don't we jump straight into it? Because it is invasive, comes with complications, and extracting a sample of tissue from the prostate needs to be from the tumor itself, so we need to exactly know where it is. The imaging plays a crucial role here. It plays the role of detecting the location of the tumor and also give further information that will help us define treatment. Treatment is not linear, so we have a tumor board. That tumor board is composed of urologists, radiologists, and the patient itself, because these treatments do not come without complications, and the patient has the right to define what kind of life they want to live. Type of treatments we have is radiation therapy, prostatectomy, which is surgery, or hormone therapy. And now you may wonder, well, we have it all figured out, don't we? Not so fast. Here, you see that in diagnosis of MR images, there's a high inter-reader variability. I mentioned PIRADS as a probability of prostate cancer. From 3, it's a score from 1 to 5. From 3 and above, you'll get a biopsy. And what you see here is that it will depend on the institution, for the same exam, what kind of PIRADS score you're going to get. And this is a problem because it means that there is inequity in the care being delivered. That the prognosis, it doesn't only depend on the patient's specific disease, it also depends on the physician that is treating them. Secondly, we have a radiologist shortage. Imaging, as I mentioned, is becoming more and more important, but the supply of radiologists is not meeting the demand because it's a high stressful job with really high stakes. Now, the problem here is that you then have delayed diagnosis. Delayed diagnosis gives time for a tumor to spread, reducing the prognosis. Radiologists, what they do, once the image is acquired, they have to understand the anatomy of the organ, segment it, understand the differences between healthy and non-healthy tissue, detect that lesion, and putting all this and clinical characteristics into consideration, output that PIRAT score. And here is where AI can play a role. Earlier this year, we've had an algorithm, FDA approved, so it means it's a medical device, that not only segments the prostate, but also detects the exact lesions. It feeds this information to the radiologist so that they can focus on the details in order to best output a PIRAT score. Now, how do we do this? Well, the algorithm for segmentation, it's an adaptation of a UNet with some deep supervision. Nope. Maybe. Well, after that, we have a clustering, there we go, the clustering algorithm. We have a clustering algorithm that, given the intensity profiles of the multiple images that come in, outputs a set of candidate lesions. Now, this is an unsupervised algorithm. Next, we have a CNN-based classifier that tells you what are the clinical, there we go, what are the positive lesions? Because of those candidate lesions, not all of them are in fact lesions. And finally, a second classifier that takes into account not only the probability of the first classifier, but also the size and the location of the lesion will tell if it's a high or moderate risk of clinically significant prostate cancer. But Bernardo, wait a second. You just said that clinical significant prostate cancer, you need biopsy for that. So how do you do this? Well, yes, we have images as input to our model, but the label, it's the results from the biopsy. And this might seem like a small detail, but it isn't. This means because what we're trying to do is to solve a clinical significant problem. We're trying to understand if the patient has, in fact, prostate cancer or not. We're not trying to write an article saying that our model is better than a radiologist at predicting PIRATs. No. So we have to understand the problem, we have to understand how the problem is defined, and use the data that will better help us solve it. Okay, we have a model. Do we have a medical device? Not so fast. We need to prove to the FDA that the model just doesn't work in our system, that is robust, and it can be deployed in a multitude of institutions and settings. So we ran a multi-reader, multi-study, fully crossed clinical trial. And this is a mouthful. I always have a hard time saying it. It basically means that we went to great extents to ensure that whatever results come out of it, they're reproducible. And the results that we'll see in a bit, yes. Although we compared radiologists unaided without a system versus radiologists with a system. And although specificity stays more or less the same, sensitivity increases by 10%, from 80 to 90%. This means that a lot of lives can be saved. Because once you diagnose, you can get on the path to treatment. Without diagnosis, you can't. And what's next? Do we need to just extrapolate this kind of model, go to a sensitivity of 100%, improve that specificity to 100%, do not miss any cases, and then we have our solution? In a bit? Not really. Because after treatment, 1 in every 3 men will have a biochemical recurrence within 10 years. Biochemical recurrence basically means that cancer will come back. Cancer coming back increases the risk of distant metastasis and increases the risk of mortality. Either I'm going too fast or nope. Well, there is a targeted treatment for biochemical recurrence. So although the prognosis is much lower, we do have this one. Aha, here it is. There is personalized management of biochemical recurrence. So although a patient might have a biochemical recurrence, which right now we can only detect with the PSA score that I mentioned ages ago, the prognosis is lower. But what if? What if we could understand from the get-go, from the first diagnosis, if a patient is at high risk of developing BCR? What if we could fine-tune our treatment in order to avoid or to diminish that risk? What if we could go from 1 in 3 to maybe 1 in 9 patients having that biochemical recurrence? That would save a lot of pain and suffering. Well, it might sound crazy, but actually we might be able to. A combination of MR data, clinical data, and AI, the image will pop up at any time. Aha, here it is. We've developed earlier this year, I think, a algorithm, we've published paper, not a medical device, and that is the difference, that can predict the risk of a patient developing biochemical recurrence, so basically having that cancer coming again. With that, we can identify these patients and say, okay, you will have a specific type of treatment. This we can do with sensitivity of 90%. This kind of information, clinicians don't have it at the moment. This kind of information can really save lives, and this kind of information really is going beyond what the eye can see. Now, you know about MR, you know about AI, radiomics, maybe you're not as familiar with, so let me talk to you a little bit about it. And there will be a diagram that might be a bit overwhelming, but we'll break it down to understand the workflow and the different steps within radiomics. Because radiomics is a field of medical imaging. Aha, here it is. It's a field of medical imaging that is growing quite a lot. And it's based on the different types of omics, and we will have a talk later today. Let's start with the blue part. Well, it is a computer vision problem, right? We have our images. So we start with the traditional image processing, normalization, resizing, cropping, whatever you prefer. Then this is one of the key steps, and this is the feature extraction. We extract features from the lesion, so we have to have a lesion segmentation beforehand, okay? These radiomics features give you information about the shape, and such as the elongation of the lesion, the size of the lesion, the specularity, basically means how spiky it is, and gives you information about the pixel values, the mean value, the maximum value, so on and so forth. It also gives you information about statistics regarding the histogram, so skewness, kurtosis, and all that. Basically, once you have your image, you extract those radiomics features, and you get a big table of tabular data. Now we're not dealing with a computer vision problem anymore. We're going to go into a more traditional, classic machine learning. So with that, you do your feature processing as standard and feature harmonization. I'm not sure if feature harmonization is an aspect more common within medical field than other domains. But feature harmonization basically means that your features or your data might have differences that are not just due to biological factors. It might also have variations because of how the image is acquired. Because you're not always using the same MR scanner. For the same MR scanner, different people will use different parameters. So you try to harmonize those. And that has a big impact in how accurate you can predict. After we've done our feature harmonization, we go into the feature selection and model selection. These two, we usually do them in tandem. Because you have thousands of images, well, hopefully, but that's not really true in medical domain. You don't have thousands of images, or rarely you do. You have thousands of features. So your model will overfit if you don't reduce them. For that, we use feature selection, standard things like interclass correlation, Pearson's correlation. We like to use one that is called minimum redundancy, maximum relevance. And these we experiment them with different models. The models, again, are pretty simple stuff. You can go from logistic regression to XG boosting, CAT boosting, whatever floats your boat, really. Radiomics brings a different approach to medical imaging, and on its own, it's really powerful. But it's even more powerful when combined with deep learning and clinical variables. Now, why don't we see more of it? Why don't we see more of the medical device that I mentioned, the one that's FDA approved and that is already in practice, being deployed? Why don't we see more of these models that go beyond current workflows? Especially when in 2016, we had one of the founding fathers of AI saying that we should stop training radiologists, that it's just completely obvious that within 5 years, deep learning is going to do better than radiologists. Well, in my opinion, this is one of the biggest misconceptions around applying AI to healthcare. Because first thing that we have to understand is that this type of problems that we're trying to solve are not just technical. We have regulatory, yes, but as I mentioned, we also don't fully understand the science. Even more, we don't understand the business. In 2016, we had some pretty decent models in computer vision, but we had close to none medical devices. We didn't even know what challenges were ahead. The systems do not operate in a vacuum. In a study from Stanford that looked into the interaction of AI and radiologists, they concluded that the observed errors in belief updating can be explained by radiologists partially underweighing the AI's information relative to their own. But why do we have this error? Is it a bit of overconfidence by the radiologist? Is it a distrust in the system they're using? Or is it just bad design of the system? That is also a possibility. Well, the consequence is that this specific algorithm that they tested did not improve all the radiologists' performance. In fact, what they concluded is that it's better to either have a radiologist alone or an AI system alone. That is better than the joint combination. So this design of interaction, we need to figure that out. And finally, the AI model alone is not a medical device. I've said that before and I'll say it again. This diagram comes from a white paper from Google. I highly recommend it to read, looking into the hidden technical debt of machine learning systems. And you see that the plumbing takes a lot of space. And I would argue that in healthcare, that is even more exacerbated. I mentioned clinical variables earlier, but you didn't see it in the medical device. In fact, you see very little to none medical devices that combine imaging with clinical variables. This is because clinical variables are in the electronic health record system, and the imaging data is in the PACS system. These two databases do not interact. And extracting information from both of them in real time when a medical device is deployed, it's an architectural nightmare. Once we start how to figure out how to incorporate these two, because they do add a lot of value, once we start to figure out how to have humans and machines interact in high-stakes, highly specialized roles, and so once we figure out not only the science, but also the economics and the financials behind medical devices, we'll be closer to deploying more models of the medical devices that I mentioned. We'll be closer to have the type of model that goes beyond the current workflow. We'll be close to understand the problem of cancer, and we will be closer to treating it. Thank you very much.